So we are looking now at our first specific example where we apply the framework for instabilities. What we're looking at here is in principle not yet a real instability, but it's a type of wave that can travel through a fluid. It's the so-called gravity waves, which they're not gravitational waves, but they're waves in the fluid, which are, however, related to gravity. And we will understand this better in a moment. But we assume basically a fluid that is at rest under a local gravitational field, and its surface is supposed to form a plane. Above the surface, we assume that there is a very thin gas with a constant pressure P2 on the surface of the fluid. So you could imagine, for instance, that this fluid could be the surface of a star, where within the star you have the fluid. Outside you have something like the corona or an atmosphere, but it's a very thin gas, and there's a relatively clear transition in between. We choose here our coordinate frame so that the surface of the fluid is the xy plane, and then we have a simplified model for the surface of a star, where of course we do not consider the full star. We can consider some part of the star where the surface looks approximately flat, which we can then treat in a more simplified way. Or what you could also imagine is an accretion disk with thin gas like a corona on top of it. And what we want to understand now is how perturbations in the fluid surface will be propagated. Now, we have to first describe the surface. Once the fluid is perturbed, then the surface is no longer a perfect plane, but there will be small perturbations. And we then describe the surface with a function psi. That is a function of the x and y coordinate and the time. And basically this function psi tells us the height of the surface at a time. So if there's no perturbations, psi is just identical to 0. But if there are perturbations, psi will have a non-zero value. And this plane is moving, or the surface is moving with the fluid. So the velocity in the z direction of the fluid, in principle, is the change of psi with time. And in principle, Vz is then given as the partial derivative of psi with respect to time. And we also have to then consider, if you change the position, or if you move along the surface, then the velocity will relate to the gradient of psi. So this is a correction that in the nonlinear regime has to be taken into account. But in the linear regime, when perturbations are small, then the product of V and gradient psi will be extremely small and will be negligible. So in principle, Vz can then be evaluated as the time derivative of xi. And of course, in addition, the velocity in the z direction can also be evaluated from the potential of the velocity. So we can also write Vz equal partial z psi. From our boundary condition, we know the external pressure, we define as P0. And using the generalized Bernoulli's law that we derived in the previous video, we have P0 equal minus rho times partial t psi plus g times psi, where our local gravitational potential is phi equal g times psi, where g is the gravitational acceleration. And for simplicity, we again assume that g is constant. So like on the Earth, we assume we have an approximately constant gravitational acceleration. if you, for instance, consider only a small height variation within the star, then you will also have an approximately constant gravitational acceleration. So it's important to say that it's a simplified model, but it captures some important ingredients on how waves propagate if there is such a gravity field. Now, since only in principle the spatial gradient of psi is relevant for the velocity, we can in principle absorb constant terms or terms that depend only on time. And this means we can renormalize psi in the way it's described here. We can replace psi with psi plus P0t over rho, where rho is constant because it's an incompressible fluid. P0 is just a constant, and t is the time. And then the equation to solve becomes very simple. We have partial t psi equal minus g psi, minus g xi. And if we take another time derivative, then and we apply to equation 30, and we divide by minus g, then the derivative of partial t xi is then, of course, on the one hand, this is z, which we can also write as partial z psi, and on the other hand, by using equation 30, it becomes minus 1 over g partial t squared psi. And this equation, we can evaluate at the coordinate where z is equal to xi. And what we also do is we make an ansatz for the solution. We assume that we have waves that propagate through the fluid, and we assume that the wave propagation is along the x direction. So then we can write psi as a function f of z times the exponential I times kx minus omega t. So we assume there's a wave-like propagation in the x direction and some dependence in the z direction, which we do not describe yet in detail. This is good. This is our ansatz. We know psi has to fulfill the Laplace equation, and in the x direction, this won't be a problem with our ansatz, but what we obtain for the z direction is a little bit less trivial. So in the z direction, we then obtain that the second derivative of f minus k square f has to be 0. And to solve this equation, it basically means that f of z is equal to f0 times the exponential of plus minus kz. And since our fluid is located at negative z coordinates, that's what we assume. And if there were no perturbations, then the plane would be the xy plane, so z equals 0. We use here the solution with the plus sign, which basically means that that for negative z coordinates, the value of f will become smaller. There's basically some sort of damping when the perturbations move downwards. And of course, physically, this makes sense. If the perturbations are in the xy plane and you move further away from it, the perturbations cannot increase suddenly. The perturbations should rather decrease. And if we insert this result together with our ansatz for the Bernoulli equation, then good, what you can work out, what you find is the dispersion relation for gravity waves, omega square equals kg, which is a relation here that always leads to a positive and real value for omega. This is very important. This is why it is not an instability. Omega always is a positive real number, and good for positive value of omega, you really have a wave. If omega was an imaginary number, then instead you could have an instability, then the perturbation could grow exponentially over time, but it's not the case here. You really have a wave, which is very important. And it's the so-called gravity wave because it's related to the gravitational acceleration g. A second important quantity you can evaluate is the group velocity. The group velocity is the partial derivative of omega with respect to k, the wave vector, which we can calculate with the partial k applied to square root of kg equals 1/2 square root of g over k. This velocity, the group velocity, is the velocity for signals to travel in the gas. And you see that basically from this relation that waves with a smaller value of k travel faster. Small k means a large length scale. So waves that are longer travel fast. Waves that are short travel more slowly. This is what this relation basically tells us. To give you an example where these waves occur, so good, they can occur under many conditions, but stars are an important example. Of course, stars are spherical, so you have to generalize this concept to a spherical situation. But in the stars, the fluid is exposed to a gravitational field. You have different types of perturbations in the surface, and they propagate through the star. And they can propagate from the surface to the core and from the core back to the surface. And in principle, you can even use and try to measure these waves to learn something about the interior of the star. This is done, what is done in helioseismology when people use this for the sun, and in astroseismology when it's really applied to stars. And it is used to try to understand what happens in the interior of the stars. So it's a very important way to learn something about stellar structure. And this just to tell you, why this instability, it's not an instability, it's a wave propagation, but why it is relevant. Our next example will then be a real instability. It will be the Rayleigh-Taylor instability, which can also occur under many conditions. And this is a real instability, which, as we will see in the next video.